Prof Amin, can you mute yourself? Boleh tak? Kita ada 3 minit lagi, Prof. Saya nak tanya berkenaan dengan AAM conference lagi.
Ya.
Boleh submit concept paper tak?
Boleh.
And then that paper will be included in ERA journal lah nanti.
Dia ada arrangement macam tu lah.
Okay, sebab itu syarat FRGS kan, dia kena ada conference and then paper
saya rasa FRGS dia kena Scopus kan?
Dia kata index.
Oh ya, macam di USM dia kena Scopus.
Sebab dia memang kalau guna takbir urus geran ni daripada KPT hanya dibenarkan untuk pembentangan kertas kerja penuh secara lisan ataupun poster yang akan menerbitkan artikel penuh terindeks sahaja. So ERA pun indeks lah.
Okay.
Okay, maybe saya contribute lah, and then not sure sama ada saya ataupun my student yang akan present. Lambat lagi kan?
Bulan 12 kan?
Hujung bulan 10 full paper submission.
Sekarang pun banyak conference.
Betul. Banyak. And then nak hantar macam IOM proceeding terindeks pun not good juga dalam Scopus or CV kan. Macam saya last year 27 proceeding berindeks Scopus. So, tapi sebab student Indonesia kan semua present last year. So 27 sekali masuk dalam my Scopus. Itu saya kata saya stop lah kot sebab tak berapa bagus lah kan.
Conference yalah dia kalau dia index in Scopus dia keluar lah kan Scopus.
Yes. Tapi tak syok lah tengok 27 straight conference yang sama kan. Tapi yalah.
Conference apa? Yes.
IOM. International Engineering yang
Apa Ahad? Ahad ke apa?
Khalid Bond.
Ahad Ali.
Ahad Ali ya. Saya committee member juga.
Oh ya ke?
Oh, yelah. Betul. Nampak Prof Komiti. Dr. Zikri lah 20 lebih juga masuk paper conference.
27.
Tapi dia kira untuk graduation, ha?
No.
Hmm?
Tak kira untuk graduation.
Oh ya kah? Kami
Ya.
as long as dia publish in scope SSCI era ataupun Scopus boleh.
That's why.
Jurnal
Sebab
saja, Prof.
Ha?
Jurnal saja. Artikel jurnal je.
Oh, conference tak kira, ha?
Conference tak
Tidak.
kira.
Kami my side pun boleh, 2 paper boleh.
Yes,
Oh, tak
betul.
boleh. Kami tak boleh, Prof. Mesti Scopus atau WUS
Scopus
saja.
journal lah.
Scopus jurnal.
Hampa lebih tinggi martabat lah.
Tapi masih guna Craigie and Morgan.
Tentu lah.
Martabat tu dah tinggi kalau kira.
Kami kalau dua my side pun okey.
Tak boleh.
Satu era kalau SSCI satu cukup. SSCI Scopus dengan era satu paper cukup. Kalau my side 2 paper. Itu keperluan PhD.
Kami tinggi lagi Prof. 2 Scopus.
Okay, is everybody back? Okay, so kita sambung Dr. Yus.
Boleh.
So we have already done. Let me show you. So we have already done the first thing. Okay, we have already done the normality test. Now we are moving to the common method bias test, which is I will show you 2 techniques. One is the marker variable technique. The other one is the full collinearity technique. Okay, marker variable technique is if you have collected additional data. So I will show you here first. Okay, here we have the R square of the model without the marker variable, right? 0.594. So what we will do is if we go to the indicators, okay, at the bottom here, you have M1, M2, and M3, correct? M1, M2, and M3. Yeah? These are the 3 items most of my PhD students will collect in their questionnaire. Okay, we call it cognitive rigidity. Yeah, cognitive rigidity, and the paper that you can refer to is the paper by Lin. Okay, so you can see. So I show you the paper by, okay. So for marker variable, we have 2 papers which are useful for you to look at. So I will show you how they present the result. Okay. The first one is Walter and Cronin 235. 235, Walter and Cronin. Okay, this is a paper in marketing. Walter and Cronin are big names in marketing. And if you see in this paper, they show you quite clearly in a table form. So every time I do workshop, they say I've not seen a paper that has done marker variable. So I show you a paper so that you cannot claim like that. So this is a table they summarize, and if you see at the bottom here, we have a marker variable. And these are the 2 items they collected as additional, not part of the model. If you see, they did not report the reliability here, right? Okay, this is the variable they have in the model. They reported all the reliability. For the marker variable, these are the 2 questions not in the model, but they collected additional. So this is one way of showing them in your write-up. Okay, the second one is this paper by Lin et al. They don't show them in a table form, but they explain them in a section called common method variance, common method bias. So here we have this section called common method variance. Okay, and this is the technique following Potsakov, McKenzie, and all. And then this is the explanation about the 3 items they use. So many of my students will use these 3 items. which comes from ORAC 2003. The variable name is cognitive rigidity. Okay, cognitive rigidity. Yeah. Okay. So first we collected these three items, and then these were used as marker indicators. Okay. And then second, this is how a method factor was created using the marker indicators as an exogenous variable predicting each endogenous. If you have 2 or 3 endogenous, you still point that and that endogenous. Okay. And now once you introduce this marker variable, now you have two models. One is the baseline model without the marker variable and the model with the marker variable. So you can compare the R square change between the baseline model and the marker variable model. You can also compare the beta values in the baseline model compared to the marker variable model. Okay, so those are things you can do for marker variable. So here we have the model, and we have these three items. We will drag and let's say I put it here. Okay, I put it on the right. Okay, this is the marker variable that we have added, and we will point the marker variable to the endogenous construct. No? So I will label this as okay. Okay. So now when we run the model, you see the R square change. If the R square changes more than 10%, you have a problem. Less than 10%, you're okay. Okay, that's how we run the analysis. So I'll click calculate PLS algorithm, and you'll get the R square is 0.597. So the change in the R square is very little, right? 0.007, 0.003, 0.003, which is less than 10%. So we can safely conclude that although we collected data from a single source, the results are not biased. The results are not biased. Yeah. Any question? Any questions on the marker variable controlling for common method bias by including marker variable?
The extra question, the marker questionnaire, we for any study we can use these three questionnaire, is it?
That depends on area of study. Yeah? If you're in psychology, they like to use a variable called social desirability. There are many other variables you can use. Look at your literature in the area of study, then you can use the marker variable accordingly. Yeah?
That means as long as the questionnaire is related to the topic we want to do, we'll do, right?
Yeah, area of research.
Okay.
Area of research. Yeah? Okay. So if the variable adds more than 10%, what you need to do is you will report your result with the marker variable included, if the R square more than 10%. If the R square less than 10%, we will delete this variable and then report the model as it is, because there's no bias, right? So we don't need to control for the marker. Right? That's how you do the analysis. Yeah, that is called marker variable analysis. Marker variable analysis. Yeah. Any questions on the marker variable analysis and reporting them? So you can, if you want to see a thesis, you can look at the folder that I shared with you. One of my PhD students more recently called Sharidatul. She has some discussion about this marker variable in her study. Okay. Any questions on this before we move to
so Prof, untuk more than 10% bias, and then you need to extend more explanation, right?
Tak perlu. Kita yang tadi kita dah draw ni kan? So I show that.
And then full stop under bias and then just stop.
Lepas tu kita kata since the marker variable added more than 10%, we will report the result with the marker controlling for the marker variable.
Okay, just cakap tu je lah, and then full stop.
Kalau if the marker variable does not add more than 10%, then we will delete this and report as usual, saying that it did not bias the result.
So then after bila bias and then what happened?
Sebab bila the increase more than 10%, when we point the variable here, it will also control for the effect, bukan?
Okay.
So we report with the marker variable. Kalau dia less than 10%, it doesn't affect, right? So we will remove the variable. Itu sajalah. Okay, so that is the marker variable technique. This can only be done if you plan for data collection. Selalunya yang attend workshop tu dia mata terkebil-kebil lah sebab dah collect data kan. You don't have a marker variable. Okay. If you have not collected the marker variable, then we will move into the other technique called this one. So I will show you. Okay, the second one is called full collinearity testing. What is meant by full collinearity is we will regress all the variable in the model. Okay, when you run the model in PLS, you will only get VIF 1, 2, 3, and 4. You will not get VIF for usage because that's the dependent variable. So we call them vertical collinearity. So what we will do now is, we already saved this file called normality. Remember? Normality. Open this file. Okay. This file, we will import into SPSS. Can you start your SPSS first? I already have it started. Okay. In your SPSS, you will open file, open data, change the extension to Excel in the full desktop, right? Okay. So this file called normality. Can you read the file into SPSS before we can run the analysis? Okay. Once you click open, just click OK. So what will happen is you get this data. Okay. So we have the data which is for the 5 variables. What we need to do is we have to now create a random variable. How do you create random variable? Let me show you how it is done. So you go under transform compute. Transform compute. Semua dah ready ke? Lepas tu nanti tinggal pula. Okay. Is everybody ready with the data? So you go under transform compute variable. Transform compute variable. Okay, we will type in random. Random. Okay. The function here, function group. Just click the all. And you will look for RV norm. RV norm. This one. RV normal. Random variable normal. Okay. Random variable normal. So you need to put in a mean value and a standard deviation value. Any mean and standard deviation value. So we will click this up. And inside the bracket, you can put any number. Let's say we put 50 and 3. Okay, you can put any number. This is a random variable, right? Okay. You only need to key in the mean value and the standard deviation. That will create a random variable for you on the right hand side. Okay. Did you get that? Let's see here. Now we have a random variable. Okay. So what we will do now is we will regress all the variables you have in your model, independent, dependent, moderating, mediating, against this common random variable. Okay, against this common random variable. So you go under analyze, regression, linear regression. Okay, analyze, regression, linear regression. Okay. So we will. The dependent variable is random and all the other variables in your model will be independent. Okay. All the other variables in your model, including the dependent variable. Huh? Okay, so once we have set up the independent and dependent, you need to click this button, statistics, and ask for collinearity. Yeah? Okay. So since we are already at this page, for those who have low R square, okay, low R square, you can consider running your regression here, asking for diagnostic, case-wise diagnostic. Then we can remove outliers to see how the result changes. Okay, for those who have low R square, we can do that in SPSS. But here we only need this collinearity diagnostic because we want the VIF. So click continue and click the button OK. You will get this result, right? So here we are only interested in this column. Can you see this column here? VIF. If the VIF is less than 5, you can conclude you don't have a common method bias. Okay, common method bias. Yeah. Any question? Okay. So you can see this in this paper. We have reported it like this. So you can see here. This is the explanation. Okay.
Prof.
Yeah.
Just wondering, if let's say we have run this we have already run this VIF analysis to identify the common method bias, do we still have to run Hammond single factor?
Hammond single factor no longer acceptable.
Oh, okay, noted.
We discussed that yesterday.
Okay,
no longer
sure.
acceptable. Okay.
Okay.
You need to do a marker variable or
Mm-hmm.
this full collinearity.
Collinearity.
For those who did not collect the marker variable, you have no choice. This is the only one.
Sure.
Prof,
Thanks, Prof.
just now when we compute the random variable, you put 50 and 3. That means when we do next time, we also can put any number 50 on 3, no issue,
any
right?
number, mean value and the standard deviation, you can decide on any number.
Okay.
Okay, so those are the two things you can do. And yesterday we discussed about this, and many editors like the first one, which is the marker variable, instead of doing this full collinearity. Okay? Those are some of the things you need to think about. Okay, so we are done with number 1 and number 2. So we have done with normality test. We are done with common method bias. So I showed you both marker variable and also full collinearity technique. And now we will move to reporting the result that we already have. In step number 3, we will report the measurement model. For measurement model, we will report convergent validity table and also the discriminant validity table. So I will show you how to report them step by step. So here we will remove the marker variable. Just now we had a marker variable, right? We remove the marker variable. Just rerun the algorithm. Just rerun the algorithm. Okay. So to get to the report, just click this button, report, open report. Open report. And here we will get the hyperlink of all the results. Okay, the first table we will need for reporting is the outer loading. Okay, can you click the outer loading? Okay, and if you click here, you can see all the loadings. So what we need to do is we need to copy this set of data. Click the Excel format. Open your Excel file, okay, and paste it in the second column, okay, like this. Okay. Paste it in the second column. So this is the result we have copied from the outer loading. So how do we report? The first column you will label as variable. This is your variable. These are the items. We will put loadings, TR and AVE. Yeah, can I do that? So we have the variable name, variable. Later we will fill up the variable name. So we have the items, loading, CR and AVE. Okay, what you do is just move this to the same column. Move all of them to the same column. And then we can change them to 3 decimal place, so that you have consistent. Okay. So we move all the loading to the same column. We need to complete the table with the variable name, CR and AVE, right? CR and AVE. So the variable name we can also copy and paste. We don't have to actually fill up the table. So go back to your result again. This is the result. We were looking at outer loadings, right? Outer loadings. Now you go to construct reliability and validity. Construct reliability and validity. So when you click this button, you get this table. What we need is the composite reliability and the AV, yeah? But we cannot copy just two. So we will copy the full table. Okay. And when you come to this table, just paste it here. Paste it here. Okay. So we don't need Chromebox Alpha and row A. Yeah? This is not needed, right? So we will delete this. What we need is these two columns called composite reliability and AVE. Yeah? So I will change this to 3 decimal place. This label here, attitude, we will copy and put it here so that you have label for your variable. COVID-19 will go here. PBC, you can, if you want, you can type in the full name, or else you can keep it the short name. So I normally like to put the full name for the variable. I normally like to put the full name for the first table, perceive behavioral control, and then in bracket put PBC. So I will pull this a bit so that you can see. And this will be subjective. So we have 5 variables: attitude, COVID-19, perceivable control, subjective norm, and usage. So those are the 5 variables we have already labeled them. And now what we do is we just copy one set at a time. This is the CR and AVE for attitude. We will copy and paste it here. And next is COVID-19. We will copy and paste it at COVID-19. PBC, we will copy and paste it in PBC. SN to this part here, SN, and finally your usage. We will copy it and paste it there. So that's how you complete your table. Once you complete the table, this is no longer required, right? So we will delete this. And I normally like to do this. Here, put the conversion. Okay. So here we have conversion, right? So this is the table representing conversion. So that's how we can label them in one Excel spreadsheet with the tab, the sheets, right? Sheet 1, sheet 2, sheet 3. So we have them all in the data. Okay, so after we have done this, you will highlight this table. Okay, highlight this table, copy. In your Microsoft Word, let me show you how it can be done. So this will be table number 1, which I normally label as measurement model. Okay, so we will change it to Times New Roman 12 and paragraph. Single. Okay. Okay, so we have table number 1, which is the measurement model. Okay. So we have already copied this, right? Okay. This table. Okay. So we copy this table and put it here. What we need to do is we will pull it a bit longer so that it's fully aligned. And we can centralize these 3 columns. Okay. So we have the table ready. So this table, when we present, you don't have all the lines. So normally what I do is you can highlight the table. Can you highlight the table? From the top to the bottom, the table. Highlight the table. What will happen is you will have this design coming up. Can you see here? Table design. Table design. Okay. Look at the table design. So when you click the table design, they will give you an option. Many tables with different color coding. Okay. So the one I normally use is this one. List table 6 colorful. So you can see how the screen shows the change. List table 6 colorful. Jumpa dah use. Yeah. So this one. So once you click this.
Ni macam Prof, ni macam kelas Microsoft Word pula.
Yalah, sebab senang. Nanti table dia cantik. Kalau buat macam ni. Okay. So once you have highlighted this, what you do is you go back to your home, remove the bold, and you can decide to remove the shading. Dia nampak macam ni. But I normally like to do like this. It's much more clearer, the table. Okay? So you can see all the values already in the table. So you have the measurement model. So if you don't want, you can also use this. So you can also do like this, which gives you black and white. So ini presentation sajalah. So at the bottom here, remember we deleted some item. We deleted some item, right? It was attitude number 5. Okay. So we put a note. Okay. ATT5, SN2, and SN3 were deleted due to no loadings. Okay. So here we have deleted SN3 and 4. Sorry, SN3 and SN4. Okay. And they were deleted because they were loaded lower than the loading 0.5. So we deleted them. So that's how you report them in a table format. In a table format. That's how you report this table called table number 1. Okay, table number 1. So what are the things you will report? Okay, in the write-up, I write here how to report. Number 1, so I will write down how you can report them before explaining. So first one is, what is? These are the questions you need to answer. Okay, these are the 4 questions you need to answer for this table. What is convergent validity? How do you assess convergent validity? What are the cut-off values you will use? And finally, what did you find? Okay, number 1, what is convergent validity? This you can copy and paste from any journal article or from the book by Umar Sekran. What Umar Sekran says is convergent validity is the extent to which item measuring the same construct load highly on that particular construct. That is the definition of convergent validity. Yeah, so you write that. No? Number two, how do you assess? Based on Hare et al. 2017, you assess convergent validity by looking at loading, AVE, and the composite reliability. Okay, here we don't give them the cut-off values. No? Number three, what are the cut-off values? Okay, loading must be greater than 0.5, 0.6, 0.7, or 0.8. Who said so? AVE must be greater than 0.5. Who said so? And finally, we have composite reliability greater than 0.7. Who is the citation? So for number three, you need citation. Number two and number three, you need citation. Okay. Number four, what did you find? Point to table number one. See table number one. All our loadings were greater than 0.5. AVE was greater than 0.5 and CR was greater than 0.7. Okay, so that is how you discuss 1, 2, 3, and 4. Any questions on the discussion? Any questions on the discussion of this table? Huh? Question, huh? Now we will move to table number 2, which is discriminant validity. Yeah. And for discriminant validity, we will put in the bracket that we are using HTMT ratio. I will make this italic. Okay. So now we are moving to table number 2, which is discriminant validity. We will report HTMT ratio. Okay, HTMT ratio. So we will go back to the report. Okay. Go back to your report. Okay. We have this tab called discriminant validity. Can you click that? Discriminant validity. Okay. Here we have three criteria, right? Fonel-Lacker, cross-loading, and HTMT ratio. The one we need is the third tab, which is the hetero-trait, mono-trait ratio. Click this one and then copy, Excel format. We will paste it in our tab number 2. So I'll put this a bit now. Change the decimal place all to 3. And here we will double click and label it as discriminant. Okay. So instead of having the name here, longer name, I normally like to put number 1, number 2, number 3, number 4, number 5. And edit here to include number 1, 2, 3, 4, 5. Let me make it bigger a bit. So here we will click and put number. Okay. So that's how you can present the table. Now we can copy this and paste it in our report, where we have this, okay? And we can pull it a bit. Okay. Again, the table formatting, we will do this. Go to table design, change it to list table 6 colorful, home, bold, and then this. Okay. And the other thing we will do here is, you see in many papers, they put this, like this. This one, Which one is this? This one. Okay, it'll be dark. This one, sorry, this one. We have to put this one. So we will put this. Okay, so that's how you present the table for discriminant validity. Sorry. Let me copy this, how to report. Okay, so this is the table you developed for the discriminant validity, and how do you report? These are the four same question we answered for convergent validity. Now we will talk about what is discriminant validity. How do you assess? We have Cornell Lacker, we have cross-loading and HTMT. So we will use HTMT. Okay. What are the cutoff values? Since our measures are all dissimilar, okay, all the measures are dissimilar, the cutoff value will be HTMT 0.85, HTMT 0.85, and then we point to table number 2. All the values are less than 0.85, so we don't have an issue called we don't have an issue called discriminant validity. Any question? So table 1 and table 2 taken together, they will tell us the measurement model is valid and reliable. That's it. Okay. Then only we can test the structural model. Before this, we cannot move to the next stage called structural model. So you don't pass first stage, you cannot move to the next stage. That's how the measurement model and structural model are interrelated. Yeah. Any questions on the reporting so far? Okay. Anybody else? Any question? Okay. So that's how you report your table. So these two tables you will see in most smart PLS papers. For those who are doing AMOS, they will present the Fornell and Lacker for this part here. Okay. If you still want to do HTMT, then you need to add on a plugin from the guy called James Gaskin. Then you can also get HTMT for AMOS. Okay, you need a plugin. That's it. Okay, so that's table 1 and table 2. So you can also see them in this paper, right? Okay, this sample paper that I've given you. You see the table, right? The same table we developed. Okay. And for discriminant validity, you will have a table like this. Okay, the same table that we have developed. Okay, and explanation, they are actually here. In this paper, we have first order and second order, so the it's different. So the explanation is still the same. Citation, you have here, Hare et al. 2019. Now we have a book by Hare in 2021. Hair et al. 2021. So you can change that. Franke and Sastet is 2019. So I've given you this explanation. Yeah. Okay. So they are done with measurement model. We are done with measurement model. Now we will move to structural model. Yeah. Any questions on measurement model before we move to the structural model? Yeah. No question? The other things you get in your output, let me just quickly go through them. We have this model fit. Okay. Model fit. So if you go to model fit, can you go to model fit? Okay. In model fit now, the software gives you two types of fit. Okay. We have the saturated and estimated. Okay. What is meant by saturated is measurement model. Saturated is measurement model. Estimated is structural model. So we have a measurement model fit. We have a structural model fit. Okay. How do you know they are fit or not? Okay. SRMR must be less than equals to 0.08. SRMR must be less than equals to 0.08. NFI must be greater or equals to 0.9. So this one we fail, NFI. SRMR is okay, but NFI we fail. Okay. RMS data should be between 0.12 and 0.17. This is already greater than 0.17. So based on these values, if you run consistent PLS, you need to report this. But for traditional PLS, we will not interpret this. But I'm just telling you how to look at the numbers. Yeah. Okay. Okay. The other button you have here is called model selection criteria. Okay. Model selection criteria. Okay. Remember we were talking about competing models. Now in Smart PLS also we can do competing models. So you can have one model, then you run your fit values here, which gives you this AIC, CAIC, BIC. We can run another competing model, calculate the same values and compare. The values which are lower means the model is much better compared to another model. So those are also available in Smart PLS called model selection criteria. Okay. This button here called outer weights is only useful if you have formative measurement. If you have reflective measurement, ignore them. Ignore them. Okay. Under the collinearity, we have two tabs. Number one is called the outer VIF. You see here red color, right? Can you see the red color? Why is it red? Is because the VIF is greater than 5. Don't have to look because these are reflective items. Reflective items. Jumpa dah, use collinearity. Okay. So for reflective item, the VIF will be high. So we cannot interpret. We only interpret the inner VIF. What is inner VIF? We have 4 independent variable, 1 dependent variable, right? So they give you the VIF for the independent variable. All of them are less than 5, so the color will be green. Okay, the color will be green. So that's how you interpret most of these values. And the other number they give you is for F square. If you click the F square, they will give you effect size for the 4 independent variable. Okay, 2 of the independent variable has medium effect size, which is green, and 1 has a black effect size, which is small. 0 to 0.14 will be black. 0.15 and above will be green. Okay, and the red means not significant. The red one is not significant. Okay, so those are some of the tabs that you have in this output for interpretation. Okay, so any questions on all these tabs that's available here, this side there, quality criteria.
Prof, later we need to report all this.
No, you don't have to, but VIF we need to report.
Okay.
VIF you need to report, but the rest, like F square also we will report when we do the structural model. Structural model. Huh?
What is conventional and consistent PLS? What is the difference?
Consistent PLS is confirmatory. Like you run in AMOS, we will use a common factor, whereas now we are doing, what we are doing now is called the composite factor. So they are slightly different. So we will not look at the consistent PLS. We are not trying to fit our data to a theory. We are actually testing relationship or prediction. Prediction.
That's why we no need to report lah.
Fit values, yeah. If you want to do fit values, you better stick to AMOS because AMOS has more fit values. Here we have only 3, remember? We have SRMR, NFI, and RMS data. Whereas in AMOS, we have parsimonious fit, we have incremental fit, and absolute fit, right? Okay, we have many criteria. That will be better if you want to do model fitting. Okay, stick to AMOS. Don't use Smart PLS. Okay, so any other questions on the interpretation before we move on to the next step called the structural model? For structural model, the items are no longer useful. So what we can do is, if you have a big model, you can press the button Control A, and press Alternate X, ALTX. That will hide your items. Can you see that? Control A, alternate X. That will hide the item. So what we are interested now is, we have 4 hypotheses that we want to test. We want to see which hypothesis is significant, which hypotheses are not significant. So the beta values, if you see, this is quite strong, this is a bit moderate, and this is quite strong. This is the one we are not sure yet. Okay, 0.067. This is below 0.1. So we need to run a procedure called bootstrapping. Okay, so we will click calculate. Okay, calculate bootstrapping. Okay. And in bootstrapping, we will do 5,000 resample. This is given in the book by Hare et al. 5,000 resample. We will pick complete bootstrapping. Okay, complete bootstrapping. Confidence interval method, there are 3 methods. But unfortunately, most researchers only use the third one, which is bias corrected and accelerated. And finally, we will click the button one tail because we want to test at a one tail. Okay, so those are the options you need to set. Then you can click the start calculation to get the result. Okay.
Prof use. Just now, Prof Ramaya mentioned we have to press Control A, alternate X. S ke S? My one, I think the data still there. Prof use.
Yes, saya. Control A, alternate X kan?
X Control A, alternate X. It doesn't. It doesn't.
Tak jadi lah. Tak keluar lah.
No, the data still there. It didn't.
Yeah.
It didn't hide.
The data still there.
The item is still there.
Yeah.
Oh, alternate X. Okay, I know already. Alternate X.
ALTX, ALTX.
Okay, I do one by one. I cannot. Just now, Prof just did everything one. Okay. Then I go to
Control A.
Control
Alternate
A.
C is to show. Alternate C.
3,000. Then
X.
complete bias one tail. Okay.
Okay, Ching, okay?
Okay, okay.
Okay. So this is the result you will get. Okay, again, you will get slightly different numbers. Don't worry, because we are running bootstrapping, right? Random resample. Okay, I get 5.29. You dapat berapa?
Not yet, not yet. Still running. Very slow.
5.348.
5.35 or 5.1. So it will be slightly higher or slightly lower. That's how the values you get. So how do you know whether it is significant or not? It depends on your hypothesis. Is this one tail or two tail? If it's one tail, the cutoff value is 1.645. For two tail is 1.96. Okay, 1.96. So we decide. And my suggestion is for all analysis, you should stick to one tail. Independent, dependent, moderator, mediator, all we can stick to one tail. So I will tell you when we discuss about mediation, I give you some citation and how to write your hypothesis for one tail also. So I give you some example that you can see clearly. So since our hypothesis test is one tail, the cutoff value is 1.645. Any t value greater than 1.645 is significant. Anything less than 1.645, they are not significant. So here, attitude is significant. There's a positive relationship between attitude and intention. Perceived behavioral control and usage, that's also positive. For COVID-19, fear of COVID-19 and usage, they are also significant and positive. So 1, 3, and 4 significant. Number 2, not significant. That's how you interpret the result. Okay, that's how you interpret the result. Okay, so this is what we call as the graphical output. Graphical output. So the text output, you click this button, report. Can you click the report? Okay. So now we get this. Let me pull this out. Okay. So this is the result you got just now. You saw on the diagram. They actually given in the text. Okay. We have this t value which is slightly different, right? Everybody has a different number because of this standard deviation. If your standard deviation is higher than the value I have, your t value will be smaller. Okay. If you have a smaller standard deviation here, your t value will be higher. So the reason why we get different t values is because the standard deviation here is calculated from the 5,000 bootstrap sample. 5,000 bootstrap sample. So if you rerun this, you will get a different number. That's a common issue. So if you have an examiner who don't know, you have to explain to them what is the function called bootstrapping. How does it work? You write that clearly in chapter 3, because we have seen a situation at Viva. In UUM, what happened was there was a ustad who was the examiner for a student. The sample size was 120. Okay, sample size 120. He ran a bootstrapping 5,000. And then the ustad said, this bootstrapping is haram because you are increasing your sample size from 120 to 5,000. You are not increasing your sample size. You are only resampling 5,000 times. Okay, resampling 5,000 times. We also have people like that because they are not familiar with statistics. So they are thinking that now your 120 sample, you are increasing to 5,000 sample. We are not doing that. We are only increasing the resampling. So that's how you interpret these values. So for reporting, I will now show you how to report them. Like yesterday we talked about it. We will extend the reporting to include confidence interval. We will also include effect size in the reporting so that you can see how we can report. So we will click this table, Excel format. Okay, so I will now go to tab number 3, which I will label as structural. After you copy, paste in the second column. So I make it bigger a bit so that you can see. In the second column, so you can see much more clearer here. Okay, yeah. So let's say this is the output we copied from here. So we go back here. This is the one we copied now. Okay. As part of the reporting, we also need this tab called confidence interval bias corrected. Okay, confidence interval bias corrected. Now, so click this and then Excel format. In your Excel, we will paste it here. But we only need these two columns, which is the lower limit and the upper limit. Okay, lower limit and the upper limit. Okay, so we will copy this and put it here. Okay, so we are done with the bias corrected confidence interval. So we have now extended to report the lower limit and the upper limit. Okay. The other report we need is called F squared. Can you go to F squared? F squared. So when you click the F squared, we need this first column. First column, which we already saw just now in the algorithm, remember? In the algorithm, we have them in one column. So we copy this Excel format. So when we come here, we will paste it here first. And we just copy the first column and put it there. Okay, that. Okay. So that's how we get those values. So this is the table that we will start editing. So I will show you how you can do that. So out of these many columns, yesterday we already talked about this. We have a column called sample mean. Remember? Sample mean? We will delete that. This is the 5,000 bootstrap we ran. So we will delete this. Okay, the first column we will label as standardized beta. This will be standard deviation, t-value, BCILL, BCIUL, and F squared. Okay. See that? So the first column, we will put hypothesis. So we put H1, H2, H3, and H4. And this will be relationship. We will change all the decimal place to 3. And again here, the p-value which is 0.000, you don't report 0.000, you report as p less than 0.01, okay? So I will copy this. Okay, that's how we complete the table. Yeah. Okay, so I will write here. This is called the statistical Okay, so yesterday we also talked about the same issue called statistical significance and substantive significance. So statistical significance is denoted by your p-value, and substantive significance, which is considered the importance of the variable, is denoted by effect size, F squared. Okay, F squared. So yesterday we also talked about effect size. We have 3 levels. 0.02 is small, 0.15 is medium, and 0.35 is large. Okay, so this is medium. And let me write down. Huh? So this is medium effect. This is medium effect. This is small effect, and this one no effect. Okay. Yeah. Okay. So any questions on the table reporting? Huh? The table reporting. Huh? So this is the full table that you can report for your hypothesis testing. For your hypothesis testing. Any questions?
Prof, so you look at the substantive significance. If let's say the statistically significant, but it's still no effect, so means what that's because of the sample size only?
Yes, yes. Sample size is the one influencing this column, right?
Yeah.
This one is not affected by sample size.
Because I remember you did mention for this, we assume 0.15 because there is no meta-analysis. And yet we came out this result.
That one is different. That one is for sample size calculation. The effect size in the population. We fix at 0.15. But here we are looking at effect size of the relationship.
Oh.
Okay.
Sorry.
From your result, we compare against 0.02, 0.15, and 0.35. The minimum level needed is 0.02. Anything less than 0.02, like here, this is no effect. Okay, so I put a red color. Okay. Yeah. And you can also see here, for variables which are significant, normally your lower limit will be negative, upper limit positive, or lower limit positive, upper limit negative. Those are when the variable is not significant. When the variable is not significant. Yeah. Any questions on the reporting? So this is the full report that you can present for your analysis. Okay. Any questions? Okay, here we can see the table in the paper that I showed you. So I will make it big, smaller a bit now. Oh. Okay, yeah. So you can see the same table. Only thing, you have the VIF, right? So the VIF you can report in the text. I no longer report them in the column. So I normally stop now at effect size. Tak ada ni ya. Yang ni tulis dalam teks sajalah. Okay. Any questions on the reporting? So this is the most complete, and I will show you another reporting which is blindfolding and also PLS predict. PLS predict. So two different things. Yeah. Okay, semua. Any questions before we move on to blindfolding and PLS predict? That's all.
Prof, this is for the thesis report writing or is a manuscript writing?
This manuscript the same. To me, you should have the same reporting procedure. Okay. Next, we will look at this procedure called blindfolding, which gives you the big Q square. So this is also reported by many researchers. I've also started stopping to report this Q square because it has been criticized. But I will show you how it is done. For blindfolding, we will run a procedure called blindfolding to set an omission distance. The omission distance from the simulation, they have already suggested any number from 5 to 12. Any number from 5 to 12. The only problem with blindfolding is we will remove items, not the case. We will remove item, not the case. What is meant by item is we have item 1, item 2, item 3, item 4, item 5, item 6, data, right? Your data points. We will move, if your distance is 3, we will remove item number 1 plus 3, right? Item number 4, 7, 10, and so on. If your distance is 5, you will remove item number 1, item number 6, item number 11, and so on. So that's how this data is removed. And what they will do is they will try to replace the number by running your PLS algorithm. Okay. Based on the algorithm, we will try to replace a number and see what is the difference between your actual number and the replaced number. Okay. So this is where you will calculate a value called Q square. If the Q square is greater than 0, then you have predictive relevance. So this is from the citation of Fornell and Cha. Fornell and Cha. Okay. So I normally report in my tax report R square was 0.714, and in the bracket I put the Q square equals to a certain number. Okay, just in case a reviewer asks. So you can see in this reporting, I normally report them like this. Yeah. So you see R square was 0.409 and the Q square is equals to 0.201. This is blindfolding. Okay, blindfolding. So how do you get the value which is the big Q square is in your report here. Okay, when you run, you will go under calculate. There's another tab called blindfolding. Okay, blindfolding. So for blindfolding, they will ask you for the omission distance. It is always better to put a bigger number. So the number suggested is any number from 5 to 12. Okay, 5 to 12. So we can put a number, say 9. If you put a number that is not suitable, the software will put a red stop, and it will not run. Okay, any number which is not suitable. Okay, we will put an omission distance of 9 and then start calculation. So this is what we call as the big Q square, cross-validated redundancy. As long as the number is greater than 0, you have predictive relevance. If the Q square is smaller than 0, you don't have predictive relevance. That's all. Okay, that's all. Yeah. Any question on blindfolding?
Prof, this means predictive relevant means the structure can be used to predict lah. Is it?
No, but the criticism to this analysis is you are not removing the case. You are removing only item. Remember here?
I don't understand. Actually, what is this blind folding?
You are removing this item and then you want to predict this item. When you run your model, you have an equation, right? Y equals to A plus B1, X1, B2, X2, right?
Mm-hmm.
So you now replace the X1 and see what is your Y value. So you are actually trying to do the replacement and see whether the value that you calculate with the equation and the actual value are similar or not. Remember in your regression, we have a Y and a Y hat. Yang Y topi itu kan? Y is your actual Y. Y hat is the estimated Y. Okay? When you take the y minus your estimated y, in some situation the difference will be negative. In some situation the difference will be positive. In some situation the difference will be zero. So that's what we are trying to do in this analysis called blindfolding. Whether we can actually predict the item. So this is item. We have another technique called PLS predict, which will predict the dependent variable. Okay, so that's for blindfolding. So done. So next we will look at this analysis called PLS predict, which is now a standard reporting procedure in PLS analysis. Does not matter you are doing a thesis or you are doing a manuscript. This is now becoming important. This is the lady who developed this technique called PLS predict. Her name is Galit Shamiali. She's now working in Taiwan. Okay, and I actually met her for the first time in 2015 when I went to Sevilla for the PLS symposium. Suddenly you saw a lady sitting in the keynote, the plenary session with Joe Hare, Ed Rigdon, and Theo Dijkstra. Okay, never heard of her. I've never cited her at all before that. So I started to do some search on the internet and then found that she's actually a big name in big data analytics. Okay, big data analytics. So that's why we are not very familiar with the name. So she came to the conference to talk about this technique called PLS predict. So in big data analytics, when you say prediction, you must be able to predict out of sample. That means if you have a new data set you collect, can we predict that sample? That is what is called prediction. So in the blindfolding, you're only removing item. So that is why she said this is actually not a good technique. She came out with this method called PLS predict from this paper. This is the paper that started this thinking about a new method called PLS predict. And the title is very interesting, right? The elephant in the room, predictive performance of PLS models. So this was published in 2016 in a journal called Journal of Business Research. But unfortunately, up to 2019, there was no metric how to assess good or bad prediction. Okay, it was not there. But what they argued here is Q square that we calculated just now called blindfolding is not truly a measure of out of sample prediction, as blindfolding does not omit entire observation but only data points. Okay, data points. So this is where they came out with a method called PLS predict. So in PLS predict, what we will do is we will fold the data. Let me show you. Okay, when we have data, let's say we have 100 cases. Sample size is 100. We will fold the data into 5 folds. 20, 20, 20, 20, and 20. Okay, so we have 100. We divide them by 5. You get 20. So this will be your first 20 cases. You will keep the first 20 cases separately. And these 80 cases, we will develop an equation, and from the equation, we will try to predict this 20. Okay, that's repetition 1. In repetition 2, we will put back the 20 from the first fold, hold out the second 20, use the remaining 80 to predict this. So we will run this 5 times with 5 repetition, 5 fold, 5 repetition. How do you decide number of fold? Depending on your sample size. If the sample size is 200 and more, you can fold 10 times. If your sample size is less than 200, you cannot fold 10 times because the minimum sample size in each fold should be 20. Okay? In our data set, we have 176 cases. Okay, 176 cases. So we cannot fold them 10 times because 176 divided by 10 is 17.6. Not enough 20. Yeah? You must have minimum 20. So we will only fold 5 times. Okay, we will only fold them 5 times. How do you know your model is predicting well or not? This is where they came out with this forecasting. From the forecasting literature, for prediction error, we can look at these 4 values. Root mean squared error, mean absolute error, mean absolute percentage error, and the Q-square blindfolding base Q-square. So the model that gives you the smaller error will be a better model. Okay, so they will give you the root mean square error for your PLS model. Now they have also developed a model called a linear model. In 2019, they developed this technique called linear model. We will compare the result from your PLS with the result from your linear model. Okay, so if your result from your PLS model error term is smaller than the linear model, then you have good prediction. If your error from your PLS is greater than your linear model, then you don't have prediction. Okay, that's how the test is done. And this is where this paper by Galit Samueli et al. In 2019 came into the picture. Okay, and this paper in European Journal of Marketing. European Journal of Marketing is one of the top journals in the world. And it took them only 8 days from the submission to acceptance. Can you read? Can you see why? Okay. One of the associate editors of this journal, her name is Dahlia Manstri. She actually came to Malaysia for a visit, and one of my students actually took her to visit me. She said, I want to meet your supervisor, one of my PhD students. And then I asked her this question, how come you accept papers so easily? Within 8 days, you accepted this paper. And then she told me this, look at the co-author. Who is the co-author? His name is Joseph Hare. And this paper will get lots of citation. And this paper is getting lots of citation. Anybody and everybody who runs PLS analysis will cite this paper when you run PLS predict. So the numbers are going, citation is increasing. Okay. So here they give you a Q square in PLS predict. We have 2 types of Q square. One is for your item, the other one is for the construct. Okay. So the starting point for your PLS predict is look at your latent variable Q square. If your latent variable Q square is less than 0, then you stop there. No more prediction. If your Q square is greater than 0, then only we will look at the error terms. Are the error terms symmetrically distributed or not symmetrically distributed? If it's symmetrically distributed, we will use the criteria called RMSE. If the errors are not symmetrically distributed, we will use MAE. Okay. So if you are a person who is easily confused, forget about everything. Just use RMSE all the time. Okay. Just use RMSE all the time. And how do you know whether your model is good or not? So we will take PLS minus LM. PLS minus LM. If all the item has a negative sign, then you have high predictive power. If all the minus will become positive sign, you have no prediction at all. So in between, we have minority and majority. What is meant by majority is 50% of your items or more has a negative value, and you have majority. If it's less than 50% of the item has a negative value, you have low predictive power. That's how we decide based on this paper. Okay, based on this paper. So I will show you how you can do this assessment to see, so that you have a better picture. So I will minimize this first. Okay, so we will go back to the data we already have. I will show you the item. So here we have 4 items in usage. We want to predict these 4 items and see how good is the prediction. So we will go under calculate. Can you go under calculate? PLS predict. PLS predict. Okay, when you go to PLS predict, here we cannot use 5. We cannot use 10-fold because 176 divided by 10 is 17.6. We need 20 minimum. Yeah. The explanation this in here. One subset must have 20 observation. So 176 divided by 10, you get 17.6. So we cannot do that. So we will change this to 5. So 176 divided by 5, you get more than 20. You get more than 20. Yeah. Okay, that's all you need to fill up in the basic setting. A number of folds and repetition. Click the button Start Calculation. Click the button Start Calculation. So you will get some results. So I will show you how you can report them. Okay. Go to the button called Report. You get a result like this, right? Is everybody on the same page? Okay. The first criteria in the assessment is this one, right? Q square predict. Q square predict. Okay. So where do you get that is here. LV prediction summary. Can you click the button LV? What is LV is latent variable. MV is measurement variable. Okay. MV is measurement variable. So you get the latent variable prediction. You see the Q square here. Okay, this is greater than 0, correct? Greater than 0. So we are here. Okay. Then only we start looking here. If it's less than 0, you stop here. You conclude no prediction. Cannot predict at all. Okay. So now we are here. The second part here. Now we want to see RMSE and MAE. So where do you get RMSE and MAE? You have to click here, MV prediction summary. Can you click MV prediction summary? Okay, just now we were looking at LV. Now we are looking at MV. So here we have the PLS and LM. Ada 2 tab, bukan? PLS and LM. Now we are looking at PLS. So here we have RMSE, MAE, MAPE, and Q2 predict. So we will copy this first. Copy this first. Okay, and we will go to tab number 4, and we will put here PLS predict. Okay, PLS predict. We will paste it here. Can you see here? And this is actually for PLS. So I type in PLS. Okay, a bit so you can see. Okay, is everybody ready? Okay. So we don't need MAPE and Q2 predict. We don't need this. So we will delete this. So we only have RMSE and MAE. Okay. Now we will go back again. Okay. Kita ada satu lagi tab kan, LM. Click the LM. Now the number will change. So you click the LM, you get a new result. Copy this and paste it here. This is repeat, right? You say sama, the repeat, kan? Kiri dan kanan kita delete dulu. We will change it to center. Okay, ini 2 tak perlu, kita delete. And this is LM, kan? Okay, we have them side by side now. And the third one we will have PLS minus LM. Okay, PLS minus LM. So we copy this paste it here. Okay, are you ready? Okay. What we want to do now is we want to take this number minus this number. Okay, so we will use a formula equals the first number minus RMSE for linear model. So the title is PLS minus LM, bukan? PLS minus LM. So item number 1 for RMSE minus this. When you press enter, you get the first one. So what you can do is boleh tarik macam ni, copy the formula, right? Copy the formula, and then when you get a plus sign here, double click, boleh? Okay, now I show you the criteria, so that you can see the criteria. Okay, so we have 3 levels, right? High predictive power, medium predictive power, and low predictive power. Okay, if you look at RMSE, based on these 3 criteria, you have low, moderate, or high. Low, medium, or high for this one.
Tak nampak, Prof.
Okay, saya besarkan sikit. Nah. Di sini. Okay, here we have kalau semua predictor is negative, all the items are negative, then you have high, dekat sini. Kalau majority, you have medium, minority, you have low. So here, semua item negative bukan? Okay, so you are actually here lah. Yang nombor 2 ni, sini, 3 out of 4 bukan? Have
Medium.
low, medium. This is medium. This is medium. Yeah, correct. Okay, macam tu lah. Any question on?
Prof, you mentioned majority means more than 50% lah.
50% and more. Sana, majority. 50% and more is majority. Less than 50% is minority. Less than 50% is minority. Yeah. So that's how you can do this. So if you see previous papers, they report like this, which is quite messy. I also did this. By the time you look at the numbers, you don't know where you are. Okay, and we were also reporting this, but now the reporting has been streamlined like this. So I normally now report only like this. So this is also not needed. So we have RMSE from the PLS model. We have RMSE from the linear model. We take the difference and then interpret this. Itu sajalah. Yang ni semua dah tak ada kan. Yang baru saya tak report ni dah. This was the previous one. Okay. Yeah. So that's how you can report your PLS predict. Okay. PLS predict. Yeah. Any questions on this analysis? So the write up, you can look at this. So I've given you some example of writing up. You don't have to follow everything. Normally I've now reduced the write up. Tak payah panjang-panjang lah. So we just compare whether we have strong small, medium, or strong predictive power. Any questions on the reporting? Anybody? Any question? Okay, so I think we will stop here for lunch, Dr. Yus, and then we will continue at 2 p.m. With the second order model.
Prof, before we break, can I make a small request? Can you show how to run the missing value using EM? I'm sorry to ask this because it's new
EM,
for me.
I think I've given you in the slides yesterday.
Yeah, you have the SPSS. Is it possible just show? Is there any like specific thing we need to choose?
No, you don't have to. You only have to pick the item that you want to analyze. Open data. Where's my... Okay, here I have this data. Let me show you data preparation. Okay, yeah. So if you want to run your missing value, you will go under analyze, and you have missing value analysis. Okay, you pick missing value analysis. You need to pick the item that has missing value. Let's say I have share 1, share 2, and share 3. Okay, one variable. And you click this button EM. Okay. Click this button expectation maximization. And yeah, so I will put a new name. Oh, missing. That will give you your new file with the inputted data. Okay. Yeah. Ching. That's all.
Yeah. Yes.
Yeah. That's how you do imputation. And then when you click continue, okay, what will happen is they will, under the window, you will have this new file called no missing. Where's the file? Yeah, this one. This one, right? No missing. So this is the inputted data that you will get. Let me see. Right? I don't know. Oh, maybe my data is not there. So let me see the data.
By right, it should include other variables also lah.
No. Only the variable you are analyzing. If you are missing value.
Oh, then I have to copy and paste in this one. Is it?
After you get your imputed data, you copy and paste into the main file.
Okay. Okay.
That's variable by variable. Okay. Okay, so we will have a break for lunch until 2 p.m. and then we will come back for the second order model and moderation and mediation. Okay, have a good lunch.
Okay, thank you so much, Prof. Okay, see you all at 2 p.m. Malaysia time.
Halo, Marian. Halo. Halo. Jam berapa mulai? Acaranya jam berapa mulai lagi? Saya juga ada kegiatan tadi. Saya ke jam 10 terus keluar lagi. Ini jam 1 bermulai ya? Enggak, jam 1 waktu apa dulu? Malaysia? Oke, oke. Sekarang istirahat kan? Ya, makasih Pak. Ya, Waalaikumsalam.